here at the LSE. It's a great pleasure to chair this inaugural lecture event. And I can introduce the speakers here. Ken Benoit, who is giving his inaugural lecture. Ken is the Professor of Quantitative Social Research Methods here at the LSE, and among a range of other things, he's currently the Principal Investigator on a 5-year ESRC-funded grant, a project on quantitative text analysis in the social sciences. Ken is going to talk for about 40 minutes. And then we have a respondent, Kenneth Cukier, who is the data editor at The Economist and co-author of Big Data, a revolution that will transform how we work, live, and think. And for those of you who are into social media, there's a hashtag for tonight's event. The hashtag is #LSEData. So over to you, Ken.
Thanks, Simon, for that introduction. I'm also very grateful to the school and the Department of Methodology for sponsoring and promoting this event, and to Ken Cukier for agreeing to be the respondent. And I can only hope that my comments tonight on the subject of big data and the social sciences will do justice to the high expectations that have been set through the participation of such esteemed colleagues. So for the next 30-40 minutes or so, I'm going to talk about the challenge of big data for the social sciences. As we instruct our students when addressing a topic, a complete answer involves clearly defining key concepts. So I'm going to begin by clarifying exactly what we mean by big data and how this might make it different from other forms of data. In fact, getting this clear understanding right is really one of the challenges I should be identifying for the social sciences in figuring out how to make best use of big data. But it's not. So in the rest of my talk, after I tell you what big data is, I'm going to identify and follow the deliberately simple structure of identifying 5 challenges for big data that the social sciences confronts. So first, what do we mean by big data? What makes it different from other forms of data? The answer to this is both simple and subtly complex. The simple answer is size. Big data is simply, quite simply, data on a scale that is so large that we cannot manage, analyze, or make sense of it using the techniques that we have applied to smaller and more traditional forms of data in the past. The more complex answer has to do with the changes in the nature of that data that enable these massively big scales, especially in the ways that the data is formatted, produced, and communicated. It's not only the size of the data, in other words, that requires us to rethink our approaches to using it for generating knowledge. It's also the manner in which this data is generated and the tools that shape how it's structured and stored. Let's take an example from social media, including social media that you might have seen when promoting this talk, which the LSE conferences did an excellent job of, on the microblogging service known as Twitter. Twitter data has been shown to contain a lot of rich information if you filter it and extract this information properly. Our own Professor Tim Newbern of social policy led a study called Reading the Riots. It was an analysis that focused on, among other things, social media usage during the 2011 London riots. I am currently involved in an EU-funded project to examine patterns of political knowledge and participation by looking at Twitter data in more than a dozen European countries around the time of the last European parliamentary elections. And as you can see here, these are some of the tweets that promoted this talk. A tweet is a snippet of text that's limited to 140 characters. But each tweet is also associated with a very large quantity of additional data. This is what we know as metadata. A single tweet, in fact, requires about 2.5 kilobytes in the format in which it's available from the Twitter Application Programmer Interface, or API. By modern standards, 2.5 kilobytes is not very much. But this is only because we've become spoiled by a wealth of computing power, with phones today that are orders of magnitude more powerful than the rocket science computing of a previous era. To put this into historical perspective, consider the Apollo guidance computer. This was used to carry astronauts across 356,000 kilometers of space from the Earth to the Moon and back. This crucial piece of computing machinery had a storage capacity of about 16 kilobytes. This would be enough to record about 6 tweets. Of course, this is not a very fair comparison, since the computers of the 1960s were hardly designed for use with modern social media. Fortunately, computing power has made huge advances, enough to handle the current daily volume of about 500 million tweets per day, from about 288 million monthly active users. This, of course, requires industrial-scale computing power, the modern equivalent of what the NASA computers were to civilians in 1968. If we take a standard desktop computer of today with, let's say, a generous 16 gigabytes of RAM, you would not be able to fit more than about 6 million tweets into active memory. That's assuming you did nothing else with your active memory. A standard 1 terabyte hard drive, which is more than 187 million times the active storage capacity of the Apollo guidance computer, would be enough to store about 400 million tweets in their raw form, assuming that nothing else was on that hard drive. That's not even enough to store a single day of Twitter data. Other examples are more mind-boggling. To give you a few, there are currently about 3 billion Google searches every day. On US equity markets, there are about 7 billion shares traded every day, about 2/3 of these traded by computer algorithms. To the video sharing service YouTube, there's about 1 hour of video uploaded every second. That is a lot of surfing squirrels and dancing cats. Online retailer Amazon.com has been known to sell over 400 items per second on its busiest days. They sold 36.8 million items on Cyber Monday alone in 2013. On the social media site Facebook, there are more than 30 billion pieces of content, which includes web links, stories, images, photos, posts, etc., shared every month. So when we talk about the big in big data, we mean that sort of big. We mean millions, billions, or more, and we are having to use a new language about gigabytes and terabytes and petabytes. These are data volumes on a truly staggering scale, on cosmological scales that defy comprehension. In this talk, I will refer a few times to astronomy because I think the astronomical scale probably best gives us some sense of the vastness of big data and of its complexity. Of course, what I want to talk to you about and what my comments are focused on is social sciences. This is my field. Furthermore, this is what the London School of Economics is. It's an institution for the social sciences, not the physical sciences, not medicine, not astronomy. When I refer in my talk to the social world, I want to distinguish it from the physical world, even though we could say this dichotomy is something of an oversimplification. By social, I mean a broad category including the economic, the political, the social, the legal, the financial, the business, the psychological, these activities, in other words, human-related activities. Much big social data comes from the byproduct of these human activities. Sometimes, as in the case of Twitter, generated by new activities that are linked to the data that we produce. But a lot of big data, by contrast, comes not from new activities, but rather from the improved measurement of existing phenomena. This is particularly true in the social sciences, in the physical sciences, and in medicine and engineering, where what we've done is improve our ability to detect and to record the physical or biological processes. This has led to a massive datafication of these processes, where here, datafication is an excellent term that I borrowed from Ken's book with Victor Meyer-Schoenberger, A Big Data, a Revolution That Will Transform How We Live, Work, and Think. Datafication refers to the process of recording information in a systematic, quantified format that can be tabulated and analyzed. Now, I have to make reference once again to the cosmological to give you a sense of the latest project to push the envelope of what is mind-boggling scale of big data. An international consortium of astronomers is currently constructing a massive telescope array called the Square Kilometre Array across parts of Australia and Africa. It's called the Square Kilometre Array because its size would be equivalent to a single satellite dish covering 1 million square meters. Comprising the biggest and most accurate radio telescope ever constructed, it's estimated that this system will generate an exabyte of information per day. An exabyte is 1 times 10 to the 18th power. That's a lot of zeros. And this is daily. This is more than twice the information transmitted on the internet every day. 1 exabyte could hold 100,000 times the printed material, or 3,000 times all of the content of the Library of Congress. If we compare this to what Google currently stores, in 2013 it was estimated that the company had about 10 exabytes stored on disk and approximately 5 exabytes stored on tape backup. Imagine having to make that tape backup. So this is data not only about astronomy I'm giving you here, but it's on an astronomical scale. We have long struggled to grasp the scale of our universe, but now the scale of our data has reached the same proportions. In fact, this SKA is so ambitious that it's not even known how they're going to store this data yet. IBM is working on this, but they don't even have a solution yet. So we're really pushing the envelope. The best parallel is probably between this project and the Human Genome Project, which to date was the world's largest collaborative scientific project, which was aimed at mapping and identifying all of the genes in the human genome. This was founded in 1990 with $3 billion in funding from the U.S. Department of Energy and the National Institutes of Health. It was expected to take 15 years. Due to advances in computing power, it actually only took 10. Today, 2015, you can sequence the entire human genome in about 3 days. In fact, there are companies where you can send your saliva and they'll send you a custom sequenced genome for a subset compared to the database for about $125 US. The world has changed, and our ability to deal with this massive data has changed. So to wrap up my characterization of big data, there's a lot more data than we are accustomed to. This is not your household consumer survey. This is not your British election study. This is not a data set about firm spending or a collection of legal decisions. It's not the results of published elections at any level, even the very smallest. You cannot email this data to a colleague. You can't even download it on your computer. This is data on an unprecedented and possibly mind-boggling massive scale. Now, I finished my introductory remarks about what data is, and I think we all know what I'm discussing, so I want to discuss my 5 challenges. The first one is the longest of the 5, because in many ways it's the most important, and this has to do with how we generate knowledge from big data. So the first point is that we need ways to reconcile the objectives of prediction and pattern recognition with the scientific goal of explanation. Big data has led to the rapid growth of a field known as data science. Data science is generally characterized as the extraction of knowledge from data, but specifically associated with the goals of prediction and pattern recognition, especially for big data. We used to call this data mining, but this was an approach that didn't get much respect in the social sciences. Rebranded, however, as data science, and using new tools and concepts from computer science, data science has become a formidable rallying cry and focal point for education, for employment, and for funding. Because of its association with big data, and it is also associated with certain kinds of extraction of knowledge from big data, it makes reconciling the kinds of knowledge that we wish to extract for social science our first challenge. In a much oversighted essay, and here I go fueling the fire, Wired magazine associate editor Chris Anderson declared an end to theory. In essence, he was saying that while our traditional objective was to understand causes, we can now be content to identify correlations with a quantity of data large enough to provide comprehensive associations of patterns without having to resort to explanation or identifying causes. Who knows why people do what they do, he wrote. The point is they do it and we can track it and measure it with unprecedented fidelity. With enough data, the numbers speak for themselves. Anderson's paragon was Google and how Google turned machine translation of natural languages on its head by using statistical models of translation rather than rule-based systems built by linguists with their knowledge of language. This was a direct extension of how Google ranked page results and searches based on the linkages of pages to similar content, not based on any human judgments of relevance. They didn't require any semantic or causal analysis. This is why Google is able to translate languages without knowing them. This is an approach that focuses on predictive accuracy rather than understanding causes. This is an approach which carries serious risks for social science, because social science seeks stable generalizations, not predictive ability that focuses on one specific training set. One of Google's many projects, and something mentioned prominently in Ken's book, is Google Flu Trends, a model of influenza occurrence that's based on search terms that are associated with flu. Around 2009, Google used its database of search results to come up with 45 terms that had a strong correlation with prediction of national flu figures. This was based on processing about 450 million different mathematical models. This sort of massive application of computing power is actually fairly typical in the field known as data science. And the following year, this Google flu trend helped to predict the H1N1 flu, or the avian flu, faster than the actual reporting of cases from the Centers for Disease Control. However, starting around 2012, this model began to fail somewhat badly. In fact, it over-predicted the incidence of flu up here by more than double the CDC estimates. Why did this happen? Writing in the science journal Science about the parable of Google flu, David Lazar and colleagues from Harvard University warned us that the quantity of data does not mean that one can ignore fundamental issues of measurement, construct validity and reliability, and dependencies among the data. They also pointed to some lessons why the Google flu predictions had failed. The problem in focusing on prediction, in contrast to explanation, is that prediction eschews a focus on causes in favor of selecting the best performing variables. Performance in the context of data science is usually very specifically defined in terms of comparing minimizing predictive error, or focusing on what computer scientists call precision and recall, which is minimizing false positives and false negatives. There are some exercises, in fact, that even give you a monetary prize for getting this right. You might have heard of the Netflix prize. This was how the American streaming video company Netflix sought to improve its algorithm for predicting which movies viewers would like. They used a data set based on their extensive set of user ratings and viewing data, and announced in 2006 a $1 million prize to the team that could improve its current predictive algorithm by reducing the mean squared error rate of prediction by at least 10%. And the team that had the lowest mean squared error would win the prize. It took 3 years for teams to reach this objective, and when the prize was finally won, it was won by a team using a method known as an ensemble of ensembles. Well, this is a technical term for basically throwing every tool, including the kitchen sink, into a massive computation search effort whose goal is to minimize predictive accuracy on the training set. And as you can see this is one of the tables from the paper of the team who had the winning entry, they really were throwing predictors that have no theoretical reason or even possibility to explain. For example, the average string length of the title, or percentage of movies with numbers in the title. Your dissertation advisor would probably be very unhappy were you to use variables like this in the theory for a social science thesis. And as an interesting consequence of the outcome, after awarding this $1 million prize in 2009, they never actually implemented the system. Netflix wrote on a blog post that we evaluated some of the new methods offline, but the additional accuracy gains that we measured did not seem to justify the engineering effort needed to bring them into a production environment. In other words, thank you very much, but it's too complicated for us as well. So how well would these methods travel to the social sciences? Well, it turns out if we overemphasize prediction, then the validity of our explanations can break down very quickly. These can lead to absurd conclusions when they are naively applied to social phenomena. Let me show you a widely reported paper by Valenzuela, Halpern, and Katz, who studied the correlation between usage of social networking sites and happiness in marriage and relationships. Using both aggregate data on divorce rates and social networking usage and individual data from surveys, they found a positive and statistically significant relationship between Facebook penetration and divorce rates. In their estimates, a 20% increase in the share of Facebook users in a given state is associated with a 4% increase in the divorce rate in the following year. Now, to be fair, and why should we be fair, the authors did acknowledge the possibility that recently divorced people and those in troubled relationships may turn to Facebook as a remedy or to find new partners. However, that did not prevent the research, leading to conclusions that social networking usage wrecks marriages. From a cause and effect perspective, SNS may reduce marriage well-being through habituation or addiction, sparking feelings of jealousy between partners or facilitating having extramarital affairs. They also said, excessive use of social media may trigger marriage unhappiness and ultimately divorce. Now, the problem here is that focusing on social media usage rates to predict divorce, they are doing nothing but speculating on the causes. And that is all that they can do in the absence of some causal identification strategy. Because of the data science association with the scientific rigor of this study, however, popular media picks up on this result, and this has even been cited in some legal cases in divorce courts. Now, in social sciences, we have long ago moved past casual approaches to causal effects. Social science, in fact, we often have a completely different goal from prediction. Our objective is usually instead to isolate and estimate marginal effects, which can be identified as causal. We do this through a careful theoretical choice of variables, not machine selection of predictors. I want to share with you two examples from my own field, which is political science. In the first, the question is whether appearing earlier on a ballot helps candidates to receive more votes. The objective in this type of study is to determine the optimal institutional design, in other words, how to let candidates appear on ballots in a way that is fair. The question is, does appearing earlier on a ballot help your votes, all other things being equal? Now, this raises a very good question. How do we hold all other things to be equal? Well, the answer in this case is actually quite easy because ballot order is effectively randomized in many contexts. In some contexts, they use alphabetical order, which is almost random. In others, random order is used. Two political scientists, Daniel Ho and Kosuke Imai, published a study in 2008 that studied ballot order from California state elections and primaries. California uses a randomized alphabet that is equivalent to a random treatment of the effect of ballot order. By drawing this random alphabet and then using that to order the candidates, they ensure that there can be no relationship between the main treatment variable and any possible confounding effects, because they cannot be correlated with something that is randomly assigned. This means that few to any additional variables need to be included in this model. But also, it means that predictive accuracy is low to non-existent. The objective here is not to maximize prediction of an outcome, but rather to use random assignment of treatment to estimate causal effects by comparing the difference in outcomes to potential outcomes, unobserved outcomes from not receiving treatment, or for the units that did receive treatment. This is done by assuming that units are equivalent with respect to everything except treatment, which is a plausible assumption when treatment is randomized. In their study, they were able to find that there was an effect, and the things up here above this zero effect bar being significant, and they found that there was a boost to being first on the ballot, and that this was greater for small parties, and it was greater in primaries than in final elections. How did they do in minimizing root mean squared error, a fancy way of saying how did their prediction do? That was the objective of the Netflix prize. Well, the answer would be terrible. In other words, this is an excellent model for estimating the causal effect of ballot ordering. It's a terrible predictive model of who wins an election. This is of no concern to us as social sciences, however, because our goal is to focus on the differential effect of a treatment, not the predictive accuracy of a model. It's the confusion about which of these objectives which was part of the key problem of the above-mentioned Facebook study, because it provided no way to distinguish correlation from causation, and therefore no way to identify causes. The particular problem in that study was that this was an observational study characterized by extreme non-random assignment of treatment, which was the level of Facebook usage, among groups that didn't take account of their levels of pre-existing marital unhappiness. And this means that the nature of the relationship is undetermined. Now, we are seldom so lucky, as in the ballot order problem, to be able to assume randomized treatment in non-experimental social science data. And in response to this challenge, social science has developed a powerful arsenal of techniques to identify causal effects from observational data, while still making similar assumptions about unit equivalence and potential outcomes. Most of these developments have originated in statistics, an intellectual field founded on the basis of probability. In my own area of political science, we draw on these tools for many studies in addition to studying ballot order effects, for example, to estimate the causal effects from campaign spending or incumbency advantage. This discussion brings me to the second challenge. We should never make inferences from data, big or small, without first understanding the process generating that data and the process by which sampling from that data occurs. Now, on this subject, I could easily devote an entirely separate lecture or a half-unit course, as this is a huge and very important topic. But here I'm going to restrict my comments to the idea of sampling and how the data generating process affects what we see and therefore what conclusions we can draw. And in particular, I want to debunk a pernicious notion that has gained a surprising appeal among big data proponents, but that is dangerously misleading. I call this the myth of N equals all. In classic sampling, we draw a randomly selected subset from a large population in order to make inference about that population. The classic reason for this sampling is that we lack the resources to obtain data about the entire population, which makes it effectively unobservable. But N equals all suggests that in the era of big data, we do have the resources to observe the population, and that we no longer need to sample from it. Instead, we can use all available data without sampling to compute population parameters directly and not have to estimate them. Quoting from Ken's own book, Big Data, and here's what it looks like, and I highly recommend this book, they state that reaching for a random sample in the age of big data is like clutching at a horsewhip in the era of the motor car. The implication is that we do not need to subject our information to sampling error if we can obtain data directly from the population. What do I mean by sampling error? Well, in the best case, this involves some random noise. In the worst case, this involves fatal bias. Because I also think that this is a serious risk from the N equals all misconception. Let me illustrate with an example known to any student of polling. Here I turn to the infamous 1936 poll taken by the Literary Digest, in which they predicted the outcome of the 1936 presidential election. Conducted largely among the magazine's own readers, the poll concluded that the Republican candidate, Alf Landon, would win in a landslide. Founded in 1890, this popular magazine Literary Digest had correctly predicted the outcomes of the previous 5 elections using its polls. The 1936 postal card poll claimed to have asked 1/4 of the nation's voters which candidate they intended to vote for. In the Literary Digest's October 31st issue, based on more than 2 million returned postal cards, it issues its prediction that the Republican presidential candidate Alfred Landon would win with 57% of the popular vote and 370 electoral votes. Well, ultimately, that's not what happened. Roosevelt won with 61% of the popular vote. The problem here was not only that Literary Digest readers and registered car owners were a biased sample, but also that there was significant non-response bias. The resulting vote estimate was therefore off target because the selection mechanism for being included in its polling was correlated with, in this case, the expression of political vote intention. The question is, would N equals all solve this? Well, if all refers to the entire Literary Digest readership base, then the answer is no. But even if the sample had been representative, there would still be the problem of the bias that comes from self-selection into the sample. In the Literary Digest poll, this meant selecting oneself to be included in the poll by returning the postal card. In studies using personally generated big data, this means the selection made by those individuals who choose to use electronic banking, who choose to use Oyster cards or fitness watches or mobile phones with GPS signals. Even if we get N equals all from every single social media user rather than a sample, we are still getting a possibly very biased population based on who is chosen to produce big data using this mechanism. Let me be very clear on one point. Don't mistake my argument as rejecting big data. Far from it. What I'm rejecting is the analysis of big data where sampling quality is equated with size and the myth that we can represent all through any data set. Recent work in collaboration between data scientists and statisticians, in fact, has led to some fascinating new ways to post-stratify samples for which significant response and selection bias would otherwise occur. In this case, the solution is not to get more data, but to combine large-scale data with an understanding of the sampling process in order to correct biases that might affect this process. In a very thought-provoking study that represents a collaboration between scholars at Columbia University and researchers at Microsoft Research, Wang et al. Used Microsoft's Xbox Live platform to target gamers and to poll them about their vote intentions in the 2012 presidential election. Using sophisticated post-stratification corrections of the sample, they were able to correct the highly non-representative sample from the Xbox poll and to do as well in their predictions as conventional and much more expensive polls. Randomly selected for inclusion prior to starting a game, people who are using the Xbox saw this screen. Now, uncorrected, these results were useless, but once the sample had been corrected, they actually tracked better during the final last few days of the election than conventional approaches. What's the lesson here? Well, the lesson is that data come from a sampling process, no matter how much of it we collect. It doesn't matter how much data we have, the numbers never speak for themselves. This brings me to my third challenge, recognizing that different forms of knowledge require different modes of inquiry. With respect to this challenge, I'm not going to speak at length, but I do not need to speak long here in order to make an important point. In social science knowledge generation, we have long recognized the need for methodological plurality, that different varieties of knowledge offer fruitful paths to greater understanding. We understand that there is no purely quantitative knowledge of the social world, and that qualitative research may be the best or even the only way to gain leverage on many important problems. Data science and the study of big data, however, is currently focused overwhelmingly on quantitative and algorithmic models rather than qualitative understanding. Yet, it is understanding many of these causal mechanisms and the context in which big data is produced and the understandings of the participants that would greatly aid us in using quantitative methods that we have long refined in the social sciences. We have no doubt all heard the social critique that data is not neutral and that the role of the observer cannot be separated from the analysis. For big data, this is more true than it has ever been. First, big data, especially data from the social world, is very frequently secondary, meaning it is generated as the byproduct of activities that were not designed by a researcher for the research purpose to which we might apply it. Second, the nature of the tools required to record and process big data invariably shape the form of that data, and this shapes the limits and the types of conclusions that we might draw. Awareness of such issues is not uniquely the purview of qualitative research, but it may provide the best context for understanding how this process and how the data content is embedded in a system that defines and produces big data. Applying the notion of reflexivity in social theory, in which theories of research should apply equally to the research itself, can help us to better understand the context and format in which big data is produced, and thereby enable us to use it more effectively to generate reliable and valuable social knowledge. Social big data, after all, differs greatly from the astronomical information that we collect through radio telescopes, because planets and stars do not opt in to usage of social media or decide whether to enable geolocation on their light wavelengths. We need trusted methods for studying social data in social context, and qualitative research here has much to offer. And the challenge for the social sciences is that data science has yet to come up with any way for integrating qualitative research in a way that we would understand and recognize from our experience in social science. It's also a problem that qualitative researchers often find the technical barriers to working with big data to be limiting. Integrating our social science toolkit with qualitative research with the technical challenges of big data, and using this fusion to improve our knowledge is therefore a key challenge. On this last challenge, I would point out an irony that much data science type research using big data as it is currently practiced has much in common with modes of qualitative research. Exploring data interactively in order to generate propositions, which are then refined through further exploration of patterns in the data, is what qualitative researchers call inductive research. Well, many data sciences might be shocked to realize that they are applying a version of what qualitative researchers term grounded theory, only with massive quantities of data and using sophisticated quantitative tools when they start with data first and questions second. The fourth challenge is ethical. We need to integrate ethical and legal understanding of the issues surrounding big data with our technical understanding. Here, the point I want to make is even shorter, but nonetheless crucial. We need to bring the expertise and understanding in the legal and ethical fields up to some rough parity with our technical understanding of big data and big data issues. Part of this has to do with maintaining standards of ethical research in the social sciences. A key part of any ethical research policy of the sort that would be needed to pass an IRB, or Institutional Review Board, involves informed consent. Yet, the private companies that record big social data are not bound by such services, especially when users have turned over or waived their rights to these things through the very liberal data-related provisions in the provider's terms of service. For providers of, quote, free services such as Google, Facebook, or Twitter, these can be very complex. How many of you have read the end-user license agreement that comes with your iPhone? Well, they essentially grant the right to these companies to use and reuse their data for their own purposes. And in the case of devices or software with location capabilities, this can include sharing your location at pretty much regular intervals. For some providers, they can use their reach and their power to conduct experiments on their users and still have this lie technically within their terms of service. In a controversial article published last year in the Proceedings of the National Academy of Sciences, Kramer, Guillory, and Hancock reported on the results of a Facebook experiment that involved manipulating the posts in people's feeds. During a one-week period in January 2012, Facebook intentionally manipulated the feeds of 689,000 English-speaking Facebook users in order to estimate whether showing more positive posts in a user's Facebook feed was an emotional contagion that would inspire them to post more positive things about himself or herself. Not surprisingly, the research found that it did, but what sparked much more discussion than the results were the ethical concerns of this experiment, of Facebook having performed this without prior consent of the people who were the users and participants in this study. They claim, of course, that it fell within the terms of service to which users had agreed when they were signing up for Facebook. Many of the end-user license agreements of big data providers push the bounds of legality, let alone ethical concerns. Recent controversies sparked by the revelations that some companies may have been sharing their data with the National Security Administration have only added to this debate. Even without that, it could be said that the ethical issues are more complex than the sum of the individual data sources. Why? Because the analysis of multiple big data sources, by linking them together, can be used to provide far more penetrating and potentially invasive portrayals than any single provider, governed by the single terms and conditions of usage. Yet, most end-user license agreements allow data to be passed quite liberally to third parties. Integrating this brave new world into policymaking and legal systems is a huge challenge. It's one that judges and lawmakers find an increasing struggle. This struggle comes not only from the difficulty of applying laws and policies that were never designed for the full-blown information age of big data, it also derives from the technical complexity of this age and the difficulties that this creates for trying to fit real cases and disputes into existing frameworks. For this adaptation to occur, policymakers and judges need some degree, and often a very high degree, of technical understanding of the aspects of big data and the world that it affects. To bring about this understanding, we, as social scientists, have a special responsibility to provide this training and education, as we are the institutions that train many lawmakers and policymakers. So here I've really made 2 points. The first is that we need to revise our ethics policies to incorporate big data usage for ethical social science research, and second, that disseminating the proper understanding of these issues, and by extension, the policy and legal implications, should also be a focus of responsible social science. The challenge here is not only setting standards for data protection and privacy, but in fitting these standards to subject matter that is new, is complex, and constantly changing. The interrelationships of big data make the complexity of this challenge greater than the sum of its parts. This plea to bring together philosophical and legal expertise with technical knowledge brings me to my last challenge of big data. The age of big data means that we will have to change the way that we work. This last challenge strikes us where we live. Now, by we, I mean social scientists especially. We privilege senior academics who are supposedly keepers of the keys to the gates of the academy and all of the expert knowledge that lies within it. Why? Because this challenge says that if we want to make sense of our changing world, then we have to change our practices. Whether we acknowledge it or not, the changing nature of the social world, which is driven largely by the explosion of big data, has devalued our most treasured asset, which is our expertise. The tools we learn in graduate school, and possibly that we still teach to our students, may be ill-suited to working with big data. This is true for the methodological approaches and true for the technological approaches as well. Re-education takes enormous energy. The ESRC just launched a Q-STEP program to improve quantitative skills in research and teaching. This was sorely needed because many institutions and students were graduating PhDs in social sciences who had little to no formal training in quantitative methods. While this program was a very positive step, the way that it is still being taught is probably a generation behind the method skills you need to get a grip on big data. Part of the problem is with us, and by us here I mean tenured research professors, because our skills are also at least a generation old. If you don't think that re-education takes enormous energy, just ask a medical professional. We all agree that it would be dangerous and irresponsible for doctors not to keep abreast of innovations in medical research. So what makes social scientists any different? On the challenge of re-education, I can hear your inner groans, especially when you're told that after taking a month of classes to learn Stata, you have to learn now Python or R or some NoSQL database, whatever that means, for your latest project, or you won't be able to work with the data. This is a challenge. But reskill and upskill is what we must do, and that includes teaching things to our students that may not be traditionally taught in social science programs. In particular, it means that no social science researcher who works with data or analyzes data can be fully data literate unless they learn some computer programming, what it is cool these days to call coding. Let me repeat that. Data literacy means computer programming. This in turn implies some knowledge of algorithms. This in turn suggests a knowledge of data structures. And taken to logical extremes, and as all competitive and advanced areas of knowledge tend to take things to their logical extremes, this means integrating computer science into social sciences. I contend that every modern institution of higher education that purports to do empirical social science research needs a computer science department. And that some exposure to this by all students should be as mandatory as learning basic math skills. Another way that we must change the way that we work means breaking down disciplinary boundaries. It has long been true that disciplines productively share, import, export research methods, with economists being perhaps the most voracious in this respect and not limiting themselves to methods. Big data makes this more true than ever before because big data respects no disciplinary boundaries. When analyzing legal or political text, for example, you might find very well that the methods you need come from genomics research. In my own work, for instance, I have read studies from fish ecology and genomics in order to develop better methodologies for quantitative text analysis. We often find our solution in Articles like this from a completely different field, where matrices of gene expressions are being decomposed using matrix factorizations and methods to extract lower dimensional patterns that have meanings that are more interpretable than the high dimensional patterns we see in the raw matrix. This is extremely similar to the problem of taking counts from a matrix of documents by word features and using the similar methods to extract patterns from that, which is something that I use in my own research. It's also something used by my colleague Cheryl Schoenhart-Bailey in government to analyze Senate debates, and it's work that I've done with my colleague Will Lowe, who's also sitting here from the University of Mannheim, where we used a parametric model of this to analyze austerity debates in Irish budgetary context. The nature of expertise, of course, is that it's very narrow. We simply lack the intellectual capacity, and let's face it, lifespans, to become experts in all fields. This points to one more area in which we should change our practices by improving collaboration, not only within our discipline, but across disciplines. Collaboration with colleagues in the areas where we are less expert often offers a means to complement our expertise and exploit synergies by breaking down disciplinary boundaries and contributing further to knowledge generation. It's also true that the complexity of big data means that we need to work openly. We're not always accustomed to working openly. And what do I mean by working openly? I mean just that, working openly and subjecting our most complex tasks to scientific scrutiny. In effect, we're opening up our work to a vast and unidentified critical audience to give them a chance to prove us wrong. Complexity makes this all the more important. Why is this? Because in dealing with complex tasks, it's not a risk that we make mistakes, it's a certainty. This is true for systems of any complexity, but the more complex the system, the more true this is. The more complex the system, the harder it is to find bugs, or, which is a term for software programming errors, or unintended consequences that might as well be bugs. There are huge advantages to tools that fall into the area that we call open source. Free, open tools that have source code available for scrutiny. Not the least of which, as a goal, is scientific replication and the basic trust that these tools work as they should. This is what open source software means, that every line of source code can not only be scrutinized, but modified by third parties. Of course, there's an app for everything, and there are outstanding free platforms for sharing computer code, applications, tools, and knowledge. This is a platform here. This is my page from GitHub, which is sometimes called the Facebook of programmers. This website fulfills three purposes. It allows people to freely distribute software, it facilitates collaboration, team-based programming, and it provides revision tracking and branching. This last system means that any user can go to this page, take my software, fork a branch. If they find a mistake, they don't have to simply tell me. They can actually fix it and integrate those changes back into the software. As both an author and a user of these tools, I respect that the technical barriers might be out of reach of many users who need them. For example, this is some of the code that Paul Nolte and I were working on last week. Not everyone can understand this, and that is the Twitter query I ran this morning. Does this look intimidating? It probably does to most of you. But there's no way around the upskilling required to work with such data. How can the data talk to us if we cannot talk to the data? This means speaking the language of the data. Speaking the language of data, like any language, involves understanding its structure. Understanding the technical basis of big data means using big data as an astronomer. Without some understanding of the technicalities, we are limited to discussing it as astrologers. Fortunately, as with collaborative open tools as GitHub, the same forces that have led to this near overwhelming complexity have also provided tools for managing this complexity. Perhaps most importantly, for bringing together the kinds of diverse expertise needed to make proper sense of it. No one who's worked with information technology or any computerized tools for analyzing data, whether big or small, has not encountered this website, Stack Exchange. This is a brilliant network of volunteer expertise sharing sites that allows the user to post questions and for experts to answer them. But these are experts not selected by anyone. but rather voted by the users and the posers of these questions and the other readers based on the value of their answers and sometimes the value of their questions. People gain different levels of reputation depending on their expertise. This has the effect of democratizing expertise, or at least leveling inequalities of access, but also in using this democratic process to ensure that the answers are complete and trustworthy. Now, as I stated when introducing this last challenge, and I'm drawing to a close now, this challenge hits us where we live because our key asset as an intellectual and university professor is expertise. Viewed more broadly, however, this process of questioning, of challenging, and improving knowledge practiced by programmers on these websites that I've shown you is really no different from the model of cumulative knowledge generation that we are supposed to embrace as scientists and scholars. This is a true meritocracy where the currency is information. Good information is recognized and rewarded, and bad information disappears. This is the sort of open, collaborative, and intellectually competitive model that we need to apply to big data to bring it into the field of social sciences. It may be unsettling to think of our knowledge as always being subject to challenge and judgment by our peers. But in fact, this has always been the nature of the scientific world of knowledge. The revolution in information and technology and communications did not introduce this process. It merely facilitated and accelerated it. Now, my own argument about our knowledge always being subject to challenges always also applies recursively, to use a programmer's term, or reflexively, to use a qualitative research term, to everything that I've just said in my talk. So I'm now going to yield the floor to my respondent, Ken Cukier, who I have no doubt will offer some insightful comments and counterpoints to my remarks.
Over to you, the other Ken.
So thank you, Ken, and thank you, Simon, for the opportunity to speak with you today. I'm honored, actually, flattered to be here and to talk about big data as a respondent. The last time I was in this venue was about 2.5 years ago when the book was published, and my co-author and I talked about the book to an audience. Was anyone there here? Good. One could possibly say we got creamed, we got slaughtered. And the reason why is because of this. Some of you may recognize the Latin. It means to understand the causes behind things, which of course is the motto of LSE. It comes from a Greek saying, probably Lucratus, but no one really knows. And it's cited in Virgil, though. And it might be evocative of that 19th century project of Francis Baconian science, in which we thought that we could find the causes to all things. And that might be somewhat of an illusion, and big data might humble us to reconsider our scientific methods and our prowess. With that, let me start by acknowledging that in some ways, to be listening to Ken was beautiful because I had to take it on the chin. There was certain things that he discussed that seems to me was waving red meat at me in terms of how I see big data, and we can have a wonderful discussion about that, a spirited one tonight. However, it came with such grace because it came from someone who's clearly a friend of big data, so I found myself agreeing with him more than questioning how I'm going to defend myself, outgunned here at LSE with a favorable audience for him. With that, let's get started. So what is big data? Clearly a question we don't want to get into because we would be here all night, and I'm glad that Ken simply acknowledged that there was something new that's happening, and it forces us to reassess our methods and how we view the world. The amount of information, of course, is growing, and that looks like it's going to be set to continue. If we understand how we thought about information in the earlier information revolution of printing, we could see that its effects were absolutely massive, right? We didn't have the scientific method before we had the printing press because we couldn't transmit ideas in quite the same way. We didn't have mass literacy. We needed printing to have a mass literate public, even at the level of the sciences, so that ideas could be disseminated. We didn't even have rules. We didn't even have laws to protect free speech prior to the printing press because there wasn't enough speech to warrant protecting. Our values changed when the technology changed, so we had an awareness of the value of free expression. And so too, I think in the world of big data, when we have vastly more data than we ever had before, so too, it's going to change the way that we think about the world, we understand the world, and how we perform science. Ken and I agree with that. Where we go with it is going to dovetail in different directions. One of the more interesting ways that people are using big data is not simply to understand it as a human being, but to enshrine in software and by using data to things that we'd like to get done that before we had to explicitly train a computer to do, that now we will be able to have the computer learn based on data and do for itself. And it's an area called machine learning. Now, Ken had referred to it as that we're taking the human being out in the idea of knowledge. That might be the case, but we're not there yet. Actually, the way that machine learning works, whether it's Google's translation or Google's PageRank system, is that the human being is still there. It's latent, but the human being is still there. So let me give you an example in terms of Google's PageRank system. The system's based on link structure. Those links were determined by a human being, i.e. someone links to lots of people link to the name of the White House at whitehouse.gov, and therefore they go to it. Likewise, the system learns by clicks, and that too is a human interaction. So there is sort of humanity involved in the machine learning algorithms that are relied on big data. In the case of Google Translate, those translations themselves are high-quality translations that human beings have done that then the machine learns by analyzing millions of them, trillions of sentences, actually billions or hundreds of billions of sentences, to know what correct translation or the correct translation of one word in one sentence is relative to another, not based on what those words are, but based on what those words are relative to other words in that sentence. Okay. So in terms of knowledge, we still have the human being somewhere instantiated somewhere in the system. And of course, the self-driving car by Google is based on a machine learning algorithm as well. So when we're thinking about big data, I want to suggest that there's lots of aspects that we are using it for that don't fit directly how a human being is going to use the information. It may be machines using that information to provide outcomes that humans used to do, such as a self-driving car. So one of the damning criticisms that Ken has presented is Google flu trends. And the reasoning is because of causality and because it seems to have failed. Okay. And it's true. In the paper that he cited by David Lazar, the joke was on Google because it did such a terrible performance. But reading the fine print of the paper reveals a nice little Easter egg, something that we should all think about. They write, the authors, does this mean that the current version of Google flu trend is not useful? No! Greater value can be obtained by combining Google flu trends with other near real-time health data. For example, combining flu trends data with lag CDC data, dynamically recalibrating flu trends, we can substantially improve on the performance of GFT or the CDC alone. See chart. Now, my heart sank when Ken talked about ensembling as a way of throwing the kitchen sink at anything to see what sticks. But here in the very paper criticizing big data by Dave Lazar and his colleagues at Harvard, what they're suggesting is ensembling. What is ensembling? You can think of it as the wisdom of crowds or the idea of group intelligence or the way that science tends to be performed in some instances. Traditionally, if you're in the world of the paradigm, you only fit, which we tend to be in the sciences, we tend to only see one color, and we ignore other hues until those other hues become so dominant that we either need to fit them into our existing model or we need to change the model, right? Classic Kuhn. In other instances, we recognize we can learn by simply, as the GitHub suggestion is, that we can bring lots of eyeballs to the problem and we can incorporate lots of different models. Now, if it goes against the paradigm, that's a problem, right? But in this instance, we were able to take two data sets that were in a way were uncorrelated. Well, they were slightly correlated. We can take two data sets, bring them together, and improve the accuracy of the prediction of either one or the other. Okay, and I think that's a useful way of seeing how big data may be implemented in society, and I think Ken would agree as well, since he has said that there is a usefulness in reaching out to using big data techniques with the traditional way that we do statistics. That brings me to the traditional way that we use statistics, the myth of n equals all, which is quote unquote dangerously misleading, that Ken has said. And he brings up 1936 poll by Literary Digest. So the problem with the Literary Digest, of course, is sample bias, right? And a bias is riddled throughout it. It is literally the textbook example. There's lots of, and we can also admit that no one can ever have all the data, right? Having all the information, it's fundamentally impossible. But n equals all is an interesting way of conceptualizing an aspiration of how we handle all the data relative to a given phenomenon rather than relying on sampling, because there's certain things that sampling can never assess. Take, for example, if you're a farmer. I should also add, Ken had given me just simply basically one-sentence lines of what he was going to say. So this is in response to him directly, but I'm sort of speaking on the hoof. But I realized I was going to have images so generic that I could tailor anything that he said into them. So don't think that I sort of had planned this and been speaking in front of a mirror for a week. So imagine we're a farmer, right? In the past, we may have looked at our data on an acreage basis. But now that sensors are basically 1/1000th of the price that they were maybe just 15 years ago, because of Moore's law, because of the great cycles of technology, we don't have to rely on that. We don't have to do it by acreage, right? We could actually do it almost by meter, right? And some places do. For a high-value crop, like in Napa Valley, where I was just 2 days ago, and so therefore slightly hungover from all the wine I've been drinking on research, they're doing just that. You know, there's every vine almost has its own sensor to understand moisture, to understand the microclimates. The benefit of that is that we can see things that sampling can't assess. We can actually ask different questions. We can learn different things. So what might those different things be? Well, there was a paper last year by Kellis at Harvard and MIT who explained it very nicely. He said that when they sample and they look at 3,500 cases, which in the medical sciences would be considered a large size sample, considering that clinical drug trials deal with several hundred people, you see 0 instances, in this case, of a gene marker that might predict schizophrenia. So there's no evidence of it, 0, right? Now, if you have 10,000 cases, you get 5 identifiers. Not statistically significant. That looks like noise. You don't know what to do with it, and typically in an academic paper, you'd throw it out, right? We all know how that works. But if you have 35,000 cases, you increase by an order of magnitude that original sample size. Now you have 62 markers, suddenly 62 instances, and suddenly that is statistically significant. You can work with that. You can learn from that. So imagine if you were designing a healthcare system, and it's 1914, and you're collecting data, right? You can't analyze it all, so you're just going to deal with the sample. In fact, the whole idea of the clinical drug trial is the average man, right? Quinlet, l'homme moyen, right? That was the world that we lived in. That was the world of statistics, right? Where we take the vast hurly-burly of the world and we reduce it down to one simple number, like a mean, and we look at the central average central theorem to analyze it. But if we can actually have every single patient's medical record for every single European citizen and American citizen, maybe we'll learn something that we couldn't learn otherwise. Now, to be sure, this might be an observational study, and it might not be a randomized control experiment. I don't think that needs to be a big problem. In fact, I'm going to put now my colleagues to the mast and say we would be remiss if we didn't use this technology and accept observational studies with all their flaws, because simply we can do that now. And if we don't, it's a heinous crime against statistics, and it's an affront to science. When science was originally, when the project of science stepped forward, there wasn't math behind it, right? When Galileo said that all of natural phenomenon could be expressed in the language of statistics, he wasn't thinking of algebra, which is basically the basic math that we were thinking about. He was just thinking of geometry, right? So the interesting thing about the scientific method is as it is adopted new techniques, it's camouflaged all of its defects in the past. And I think that in 15, 25 years, we're not even going to be having this debate. We're going to be recognizing that we can learn new things from our data that we couldn't do before, and we're going to adapt very carefully our methods around the fact that we now have all of this new information that we didn't have before. What does this mean for knowledge? As I promised you, the slide is going to be completely generic, so I have no idea what I'm going to say. Okay. The idea of quantitative versus qualitative understanding. I believe I agree with Ken that we need to bring the two in together, and it's not clear how in a world of big data we deal with qualitative information, but that we will need to. I'm sure what I had to say to his points were good, but I cannot read my handwriting. Say, yes, but now new toolkit, not be zealot like the newly converted. Okay, sure. Sounds good to me. Okay. Not designed by research. Oh yeah, quite. So that it's not designed by researchers with a research agenda. Yeah, I agree with that, but I'm not overly bothered by the fact that the data that we could be analyzing hasn't been so carefully groomed and produced by researchers by research agenda, that it's data in the wild, as they say, simply because we have to adapt our techniques around the fact that we have this new data, and it's not always going to be as pristine as we'd like. And for lots of instances, it's not necessarily going to be the qualitative data that we have. There's a huge project that we can go for on simply the quantitative data. Back again to the n equals all example. Economic policymakers around the world make their decisions on the CPI, the Consumer Price Index, which is known as the inflation rate. And there, it's based on about 80,000 prices sampled monthly by the National Statistics Bureaus, when we could actually, with scanner data and with online commerce, simply look at all prices in an economy. So we can aspire to the n equals all, and just that qualitative project is going to get us far ahead of where we are today. To the ethical issues, there I agree with Ken and think I mostly agree with Ken on the difficulty that the consent has been waived, and that is a serious problem going forward. But I would implore Ken and others to look at the big stakes involved and not the small stuff. Today, a lot of the ways that the research has been conducted, say whether it's Google flu trends, but people didn't knowingly give their consent for their clicks when they wrote sniffles and aspirin into a search window, I don't think is a big deal. And I think we should recognize what those red lines are and what are big deals. The Facebook study is deeply interesting and I think should force us to have that debate, but I come out on the other side of that debate. When the Facebook study showed that they could manipulate people's news feeds based on whether they showed people slightly more positive content or slightly more negative content in their news feed of what they were likely then to post, the difference in their behavior was between, so the likelihood that they would post either slightly more positive or slightly more negative comments themselves, or items themselves, was between 0.04% and 0.1%. Okay? These are minuscule figures, minuscule. But as the researchers themselves write later on in the paper, at the scale of Facebook, when you've got 1 billion people, even those small figures has a big effect. So it still has a huge effect, but they're very small, and I think we should recognize that. Was this a big problem or not? I don't know. Frankly, I'm not too bothered by it, and we should be thankful that the research was published after all, and not just simply behind the four walls of a business. The stakes are big, of course. Samsung's smart TV privacy policy reads remarkably like George Orwell's 1984. I'll just read the Samsung policy. Please be aware that if your spoken words include personal or other sensitive information, that information will be among the data captured and transmitted to a third party through your use of the voice recognition system. And of course, poor Winston Smith had a similar problem against the thought police who were listening or potentially listening to him at all times. So where I come out on it is I think I would rather us be have a knee-jerk belief toward leaningness towards permissiveness rather than a reluctance to go forward, because I think this is a new frontier for us that can have so many great effects. So the final point is here in terms of change, and there I think Ken makes a very compelling case that if, as he says, quote, how can the data talk to us if we cannot talk to the data, unquote. I think that's absolutely right. And like many of you, when he was talking about breaking disciplinary boundaries and working openly, we couldn't help but have this sort of nostalgia that we might have heard that same sort of thing spoken in this amphitheater 100 years ago, ever thus. But he makes a deeper point that it's more necessary than ever because of data. I'll underline that to say that it's not only is it going to be more necessary than ever, it will be a requirement for good research versus bad research. So the institutions that are too late and too hidebound and don't actually have more interdisciplinary research and don't have open code and open practices are actually going to be at a disadvantage. They're not going to be practicing modern social science. Now, I am not sure that big data, and I've written a book that really is non-scientific, right? I'm not so certain at the outset how big data dovetails with science, because I see it as eschewing causality, because causality is so hard and you want to make it, you need to do a lot of work to get it. And that there's so much to gain for when you are just simply going on the correlations, whether it's a self-driving car or Amazon's shopping cart or a Facebook study, or whether people are going to click on a box for a candidate who appears earlier up on a poll, on a ballot, rather than lower down. I don't know about causality. I think that's a big topic. But I fully agree with Ken that not only are these the classical aims of science, that doesn't have those hard and fast boundaries that are an artifact of academia, and that working openly is going to be critical. Thank you very much.
Thank you, Ken. So, we've got just over 15 minutes. Let's take questions in batches of 3. Keep the questions very short, please. And say who you are. So a gentleman here in the middle, I saw his first hand up. There's a mic coming round. The acoustics are terrible in the room, so please wait for the mic. Can you take the mic, please?
Hello, my name's Julian Fedsu. I was interested about both sides of the debate about how big data is created. and about the question about how do you monitor it, how do you manage it, what it is. What about the issues of link farms, skewing data, or algorithms or people using computer systems there to change the data on the web by affecting Facebook likes, etc., etc.? How does that impact on it and the validity of all the data?
Very good. Take another question. Gentleman at the front here.
You used to say the ambition of n equals all was really the important thing rather than the reality of achieving it, but the direction. Is the ambition really n equals all, or is the ambition n equals us?
N equals what?
Us. Third question. Any women who want to ask a question? Is it all geeky men who want to ask questions? He's not a woman, he's a man. There.
My name's Leanne, and I noticed that you mentioned the need for social scientists to get involved in computer science. I was just wondering if you had thoughts going the other way, computer scientists getting involved in social science.
That's a good question. My 11-year-old daughter at her primary school, they've introduced lunchtime classes in Python code. She's 11. Okay. Go for it, guys. How about Ken? Go first.
Well, is this on?
Yep.
Yeah, on the question of the link farm. So this is a general issue where, for example, one of the problems with the Google flu trend failure in the period that was under discussion was that they changed the way that the search algorithm works. And one of the things that Google does, if you've ever, I'm sure you've used it probably 20 times today, you type in a search term, and before you complete your search typing, it auto-suggests. In June and July of 2012 alone, they changed the search machinery 86 times, according to that article. So they are constantly changing the way that their mechanism works, and therefore that makes it hard. And link farms are the sort of the same thing. So if we think that the linkage of links, or whatever they call, predict something in a network framework, we need to make sure that those are coming from valid sources. This is true of any data analysis. It's true of big data analysis and small data analysis. On the n equals us, I'm honestly not sure what you mean. But I could say in general, I've never used non-observational data in my life, and I always would prefer more data to less data. My point was that if we think that we can reach the all, I think that that's a myth. But I don't dispute that more is better.
Let me pick up on that. This is on. Okay. So, but wouldn't there be certain categories of phenomenon where you can have, quote unquote, all the data? So let's take electronic patient records. In a nationalized health service, such as in Britain, where you can remove as much as possible selection bias because it's not only the wealthy who are attending hospitals, but it's the whole population.
No, only the sick are attending hospitals, not the whole population.
Fair enough. What about it? Well, if it's an electronic patient record, okay, so that would be sick. Then we'd have to limit it down specifically to certain ailments. So it's true that we'd be missing people who are healthy who may have that ailment, but in this case, if it would be treatment for a given ailment based on certain categories, then theoretically you would have it. And you could also conceptually imagine you could have n equals all in terms of per patient if everyone who checks in when they're born, there would not be the 1% that's out.
And then the question over here about...
Well, no, that's actually a question for Ken. Because I think there's a fundamental clash. Can you ever imagine cases in which we would have n equals all?
I don't believe in the all, I think is the difference. I think if you take a very stochastic view of the world, then each realization you see is a draw from some stochastic data generating process. And just because you have all the patient records in a hospital doesn't mean that we couldn't draw more by coming up with more patients or sending more people to the hospital or treating more people. That there could be cases where there are configurations of factors that we just haven't observed in that hospital. And if we think that just because we got everyone who went in and out of the door during a fixed period, we have all, I just don't think that that's right.
I mean, a nice example would be your research on speeches in Congress. The fact that you could observe all speeches in a parliament doesn't mean you observed all the data, because there's a restriction. The data generating process means there's a restriction on the type of speeches that could take place and who gets to speak.
But it depends on what your question is. So let's take a look. If we wanted to predict the likelihood of how a Supreme Court justice is going to vote, we might do it by looking at all Supreme Court justice Supreme Court votes. If we try to understand how people are going to purchase, what they're going to purchase at Walmarts prior to a hurricane, we'd want to look at not a sample of all the purchases at previous Walmarts, but the whole database of all purchases at Walmart. I think it depends what your question is. Now, I recognize this. You would say, well, this is not science. That is simply, chasing mercantile prediction. I would suggest that for lots of problems, that would be the approach, and you could conceptualize an N equals all situation.
What about the question of should we worry about computer scientists doing social science?
Computer scientists are very welcome in my department to come do social science. We will teach you how to do it properly. Please don't do naive social science where you look at Facebook and divorce and assume a causal relationship, especially when you don't know anything about psychology and you just decide to write a speculative paragraph because you know that it'll cause more headline media to pick up what you've said.
Yeah, but isn't this is a general concern in the natural sciences now using the data analytic techniques to answer social science questions and getting a lot of coverage for this sort of stuff.
Yeah.
And it's then very easy for us to stand and whine on the sidelines and say, but it's not a sample and where's causality and blah, blah, blah.
There was an early period when economists did this in politics, if you remember that.
They still do.
Carpetbaggers, basically. But that's why we should work together because, the advantage of the world is very complex, but the good news is you don't have to be an expert in everything. You can't, so why try? But you can find colleagues who are experts and you can combine your knowledge and act as a check on one another and come up with good collaborative research.
Great, let's take some more questions. Gentleman over here. Sorry.
Hello, my name's Peter Norman. I know that The Economist has set up a visual data unit for journalists. What do you see as the future role for journalists? And will half of the people working here possibly end up being journalists?
Okay. Question down here.
Hi, I am a student studying mathematics here, and I love programming. I also served for 2 years with the Peace Corps in West Africa, where there was no electricity or running water, and I've always been struggling to wonder how I can use my skills in programming or my interest in data to help those, to at least come up with something that would make the lives of those people who live in places where they can't even generate data because there's no electricity. So would you have any inspiration or ideas on how we can use big data to perhaps reach those people who don't even have the access to facilities that would generate data?
Excellent. And then there was a woman here, third row back.
Hi, I'm Kanya. I'm from the National Institute of Economic Social Research. Just wanted to ask, the point you mentioned about the Facebook messages and the negative, positive. So you mentioned something about minus 0.4 and 0.1 difference. I was just wondering how that was quantified. Is that a behavioural quantification? And also, you said thankfully that research was published, but isn't that exactly the ethical point that research was published, but who knows what Facebook is doing behind?
Very good. Take any or all of those.
Yeah, let me go to the Facebook one first. So there was a matrix of 4 different outcomes. So if you were shown slightly more negative, you could have, what was your likelihood of posting more negative or more positive? I guess, or more negative or more positive, could be neutral. And then if you were shown slightly more positive, your outcome of doing positive or negative. There were 4 variables, or 4 values, and the range of difference was 0.04 and 0.1%. And so that's what it had meant. So in other words, these are super minuscule amounts of likelihood to do one or another, but statistically significant because there was enough of people doing it. And I think that, and yes, that one of the questions was that at least this was being published, but not behind the 4 walls of the company. But I think there was clearly there were a lot of other ethical concerns as well. Should this research have been done at all? being the most important. Was it wrong to have manipulated people this way? What if someone was a fragile soul who may have committed suicide because they had seen slightly more negative comments, even if it was at minuscule levels? And I'm sensitive to that. I think that's absolutely right. I think we should have that healthy debate. Yet I still fall on the side of urging a permissiveness to what we do, because I fret that we're going to apply yesteryear's notions of privacy onto the great potential of this new data to solve a lot of our problems, and we're not going to harness the benefits of it. Again, we can also see this because this seems a little bit unlikely that manipulating this way would create such a calamity. And I think that we could also, in our mind, conjure up a lot worse. And so I'd rather we focus our attention on the lot worse rather than go breathless on what seems to be small beer. And I'll just finish with on journalism. I hope that everyone in this building, or half the people in the audience, do not become journalists. It will be competition. The economist usually likes competition, but not on a personal level. There's no money in it, journalism anymore. But I think that all journalists are going to have to raise their game, because we want to appeal to people like readers who are in this room. And everyone in the future, as following Ken's great wishes, is going to be learning software coding, no matter what discipline in the social sciences, at the graduate level of social sciences that they're in. If they're not, it's like not knowing how to type, or not knowing basic literacy or maths or basic statistics. You're going to have that basic familiarity with coding and how coding works, just so that you can design your own research methods. So rather than be beholden to someone in another department for your research methods, that would make no sense. So in that sense, all journalists are going to have to engage at a serious level. Journalists are going to have to engage with a public who is not only numerate, as they are today, but statistic-minded as well.
Ken, solving the world's problems.
I'll make a brief comment on that. Journalism has gotten so much better when it comes to representing data in a correct fashion in the last decade. And leading, The Economist is leading in this respect. There's some very good stuff in the Financial Times and the Guardian. The New York Times has a wonderful data editor. They do some excellent visualizations, and it's so much more honest and satisfying as a social scientist to see what's being done now versus the cringe-worthy stuff that you might have seen 10, 20 years ago. And I hope we've had a part, in discussions like this, play a part in that. In terms of this, I'm not really sure what you call it. I can't give you an easy formula for solving such deep and serious problems, but technology in a lot of ways has been able to improve the lives of people in those situations. There are, I forget what the name of it was, but there's some project, it's kind of like the Chromebook, to develop a sub $100 laptop that requires no additional components. There's the Raspberry Pi. I mean, there are ways into computing that are very inexpensive. And say what you want about Microsoft, but the Gates Foundation is doing a lot to come up with clever solutions to these exact sort of problems. That money was originally funded by technology, but it's also very technologically aware in the application of it and the solutions. And this is a good thing.
I think we've got time for a couple more questions. The gentleman here with the red tie.
A question on raising one's game. Back in the 60s, people coded, and that was maybe the only choice back in that kind of technology. We seem to be reverting in some sense to that, to getting people wanting people to code. But is there some interface that you see, or some technology that will not force people into coding, some kind of application? Do you see that?
Well, let's take one more, okay. One final one. Chat in the middle.
You seem to be sort of quite hasty, and I don't understand your sort of need for speed in dealing with the ethical considerations around the big data project. It's something that your guy, Sandy Pennington at MIT has. He sort of, let's do this and then deal with the issues afterwards. I don't understand the reason why that has to be the case.
Good questions. You guys want to tackle the first one?
I'll tackle the first one. So there's a huge industry of companies that try to make tools to make complex tasks usable without learning a new language like Java or Python or whatever it may take. And this is good in a way because it brings tools to people who may not be able to jump the technological barrier. The problem is a lot of those tools are closed and you don't really know what they're doing. And that's a very big problem for science, because in science we have to know what we're doing. We have to be able to verify that, we have to be able to check it. I can tell you in the field of text analysis where I and my colleagues do a lot of programming, original programming. I have relied on libraries written by other people, and I very frequently find mistakes in those by looking at their source code. Under the model I showed you, I can send a note or even fix it, and they may or may not get back to me. That's essential, and I know that in commercial software you've got the same thing, it's just that you can't see it. So are we willing to give up our right or ability to scrutinize these tools? That's the trade-off for making it easier.
More on the ethics.
Yeah, I mean, to be honest, I was hasty simply because there's a stopwatch and I'm going over time. So I don't treat the issue as something simplistic or something that I want to race through as a way of blowing smoke, as a smokescreen for it. In fact, in the book that I wrote with Victor, we have about maybe quarter to a third of the book is all on the negative and the downsides, the dark sides of big data. You know, he grew up in Austria, which was the front line of the Cold War. He knows very well about the Stasi and surveillance. I do too, from my own family history. That's one reason why we are both impassioned about wanting to protect it, but wanting to use this as well. When the Nazis stormed through Europe, they just simply walked into the city halls, particularly in the Netherlands, grabbed the very famously accurate and detailed civil records of the Dutch, and simply rounded up the Jews. And you could actually, and the research papers are very complete on the fact that Jews were rounded up with greater in greater numbers in places that kept better records. Okay, so the original tattoos of the concentration camp prisoners corresponded to the Hollerith machine codes of the IBM Hollerith machines. Okay, so data has always been used to abet extraordinarily ugly ends, right? I'm extremely aware of it. That's why I get so angered when you have privacy advocates looking at behavioral targeting and advertisements that seem to follow you around and think that that is the problem with big data, because it just seems so juvenile and ignorant of history that they misdirect where they should have their concerns. I think there are extremely important concerns, but we need to be focused on what those concerns are, what those red lines are, and ignore the distractions.
On that note, I'm afraid we have to wrap it up. Ken, thank you both very much. Thank you all for coming.